Hi students, welcome to HSC Earth and Environmental Science and Module 7, Climate Science. This is video number 16. We're going to have a little bit of a look at the relationship between human activity and the greenhouse gases. The learning intention for this video is to be able to investigate any influence that human activities may have had on the environment since the Industrial Revolution, and specifically in terms of increases in greenhouse gases. One of the things that I can't recommend highly enough is that you have a little bit of a look at Dr. Karl's little book of climate change science. It's just packed full of some fantastic science around our whole study of climate change, greenhouse gases, which ones are important and why, and also some of the interesting debates that have occurred around this very important subject. And I think Dr. Karl is a very clear communicator, but he's also very good at being able to make often very complex ideas and issues and concepts in science very accessible. So he's definitely worth a read. I'm not going to go through the entire timeline that he's put together because I think this is definitely something to look at in a little bit more detail. What I will say though is that we have to talk about what impact the Industrial Revolution has had on the climate. And so that means we've got to go back a fair way, and we can. So the Medici Meteorological Network were actually the first weather service. They were measuring air temperature continuously for 16 years. And this meant we had a little bit of data right back in the 17th century. You can see photos and pictures of very old devices that were used in weather monitoring, some very old thermometers. And you can see that this is something that humans have been doing for some time. We've always taken a bit of an interest in the weather. As we move forward, we push through that Industrial Revolution and we get through into the 19th century. And we see now that we've got scientists that are actually starting to make the link between levels of carbon dioxide and the fact that the atmosphere traps heat. So you can see a nice little cycle here, which is culminating in Higgbom's explanation of the carbon cycle. And so we're understanding more about what's actually going on in the atmosphere, what sort of things we might be doing that may perhaps contribute to some of the warming that we're seeing in the atmosphere, and whether or not the shift into an industrial age has actually had any impact on the atmosphere beyond the obvious polluting qualities that it certainly seemed to have at the time. Those of you who also do chemistry would probably be familiar with the name Arrhenius, and he certainly had something else to say about the whole situation with climate science as well. And importantly, in 1958, and something we'll talk about a little bit more in this video, is the Keeling Curve. And that curve was, or those records for carbon dioxide levels, were started in 1958. And they've actually been carried through two generations of the Keeling family that have given us some very, very good data, particularly around in the air around Hawaii, Mauna Loa in particular. One of the interesting stories that Dr. Karl has picked up is this whole area around the early 1970s of insurance companies starting to get a little bit alarmed. Now, if you think back to some of the disasters that have occurred this year and over the last couple of years, particularly in terms of bushfires and also flooding, insurance companies have to be very, very careful that they're not insuring too many people in disaster-prone areas that is going to end up sending them broke. So I think the fact that, and he thought that was a very interesting point to make, that even as far back as 1973, insurance companies were already starting to get a little bit alarmed about what the potential consequences of global warming might be. He also praises big fossil fuel for taking a step forward into this space and to actually move the science further forward. What we ultimately got to was what's colloquially referred to as the hockey stick graph. And unfortunately, that's where Dr. Karl's bouquets end and some of the brickbats begin. And that really was the point that started off a bit of an avalanche of misinformation and contrary information to try and counter some of the very obvious concerning changes that were part of this hockey stick graph. And you can see lots of normal fluctuations. We've talked about the natural greenhouse effect and the fact that the temperature isn't stable all the time. It does fluctuate. but at a time very recently, coinciding incidentally with that period of industrial revolution where we really shifted across into some serious large-scale machine-driven labour-saving devices, that we've actually seen these massive increases. Most of those devices, of course, powered by coal or the burning of coal to create steam to power turbines, and that has led to this massive increase in carbon dioxide levels. So the greenhouse gas family, why are they important? Why does this matter? Why do these particular chemicals have so much of an influence in the atmosphere when they're in such tiny actual amounts? One of the ways we can try and understand this is to actually make some little chemical models. Now, the atmosphere itself is dominated by two main gases, nitrogen and oxygen. And here's a little molecule, or a little representation of a molecule of oxygen. Now, oxygen contains two oxygen atoms, and they're bonded together. In between these two oxygen atoms, there's a region of electrons, a little electron density, a cloud, you might like to say. And so as a result of that, there is a region that may pick up certain types of electromagnetic radiation. And so the molecule is potentially susceptible to these sorts of things. And if it does pick up some infrared radiation or other types of electromagnetic radiation, then it may cause those electrons to vibrate and you get some wiggling. But you don't get too much when you only have two atoms. So the two atoms that we find in oxygen and the two atoms that we find in nitrogen don't tend to do too much wiggling. On the other hand, all of these greenhouse gas family members have at least 3 atoms. Some have 5. And the problem is that when you have more than 2 atoms, you now have some places where the electrons can, in the little regions between the atoms, can now absorb some of that reflected radiation from the surface of the Earth. So the radiation that comes in hits the surface and converts to a slightly longer wavelength, often infrared radiation. And what it does is it makes these little guys do a bit of Pilates. So they start to wiggle in different frames. They can also move backwards and forwards a little. I can't really show that with the model kits, but they do all sorts of wiggling and wobbling around. Now, what happens is that the energy that they absorb in their bonds then gets re-radiated. Now, that's no different to any object really radiating energy. But the thing that's interesting is if they weren't there, then that radiated energy, or some of it anyway, would just pass straight back into space. The fact that they absorb some of that energy and then re-radiate it again means we know with radiation that it goes out in all directions. So some of it will go into space, but some of it will come back down towards the Earth's surface, or some of it will go out into other parts of the atmosphere. And this is the problem. The more of these molecules that you have, the more of that infrared radiation is going to be absorbed by those molecules and then re-radiated again afterwards, which keeps more of the energy, more of that heat in the atmosphere and less going back into space. On some generalized figures, carbon dioxide traps about 66% of the total heat, methane about 16, CFCs around 12, nitrous oxide 6. The problem is that we're not comparing apples and apples. We're actually comparing different molecules that have different abilities to absorb and then re-radiate energy. And actually methane is much better at doing that. It's worse, if you prefer to call it that, than carbon dioxide. So it's not simply a case of looking at each of these chemicals and trying to figure out what's going on with them. It's also a case of trying to figure out exactly how they interact with infrared radiation and what they do with that energy once they've absorbed it, how they re-radiate it again. Now, it's not necessary for you to have a strong chemistry background to understand and explain what's going on at a molecular level, certainly in terms of the exchange of infrared radiation. But it is probably important to at least understand that these types of molecules are slightly different to the 99% of the atmosphere that's made up of nitrogen and oxygen. And so therefore there's some slightly different things that are happening to electromagnetic radiation that's coming into the Earth from the sun and the radiation that's going back after it's been converted or reflected off the surface of the Earth. So this brings us to the Keeling Curve, and it's a good way to just kind of pull a few things together here. The Industrial Revolution, as I mentioned earlier, was the point where we had large-scale labour-saving machinery, and this machinery was primarily powered by steam, which was generated by the burning of coal. We had huge amounts of pollution being produced as a result of the burning of the coal, but then we also had an increase in the carbon dioxide levels. So if you're specifically looking for data that you can track through from pre-industrial revolution times where the levels were probably around about the 280 parts per million, we can see how that has changed, and the change has been such a rapid one. And this is one of the points that we've been trying to emphasize through these videos. It's not that these values are changing. That's not the unusual thing. It's not unusual for these values to change. What's unusual is the rate at which they are changing. And you can see to go from pre-industrial revolution levels of 280 parts per million up to very recent records of 415 parts per million, and most of the data that's come from here has come from the Keeling Curve at Mauna Loa. And as a result of that, we've been able to see these little fluctuations. You notice that the curve isn't a nice smooth line. There's different readings that represent different seasonal records of each of these different values, but you can see a very, very clear trend. One of the things that we want you to make sure that you can do when you're looking at this sort of data is to start saying, A, can I identify a trend? Is there any identifiable trend here? If there is, can I describe that trend? What's actually happening? How is that trend established? How fast is it moving? At what rate is it increasing, decreasing? And then can I explain that? Is there anything that I can draw on to help me explain this curve? I guess the saddest thing, the most concerning thing about the Keeling Curve is it's still going up. So despite the fact that we've had a lot of information for a long period of time, we just haven't at this stage been able to do anything significant that's starting to turn around this very concerning problem of rising carbon dioxide levels. Thanks for watching.